Now? Yes. Yes, so I shouldn't thank the organizers too much because then I'll start crying. I'm so happy to actually be in a room with mathematicians. And I really am going to start crying. And to be able to write on a blackboard. So excuse me, but I will not use slides. So it will be messy and I will not be able to say so much, but I am going to enjoy so much writing on a blackboard. Okay, so what I want to talk about is what I call algebraic / categorical / well, or maybe I should say and duality. In logic. Well, so this is what I want to talk about, methods. And the point is that if you look in propositional logic, and this has been very powerful and very useful and has been very much used. So at the basis, what it provides for you is semantics. And this is, of course, very good. But also it's really useful as a technical tool, okay, for proving lots of theorems. Now, in first order logic, if you try to do it just really algebraic with cylindric algebras or something, it kind of works. But if you look at it with category theory, then it's beautiful, right? I'm sure you will agree with that. So that's why I'm saying /, okay? Just so we belong in the same place, because I'm probably more of an algebraist, not a category theorist, but this way we have a common ground. And this gives very beautiful semantics, but I would put a question mark to this so far. Maybe I'm wrong, but you know, I'm talking about things like proving interpolation, proving admissibility of deduction rules, being able to compare different logics in a family of logics, like modal logics with different axioms, or intermediate logics between intuitionistic and classical logic, right? These are studied very much at the propositional level, and their algebraic semantics and duality are very, very, very useful in the form, for example, of cryptic semantics and so on. But as far as I know, this is not working here. And in fact, in first order logic, there are lots of things that are not known. Maximova proved that the linear hiding algebras have interpolation, okay? But the corresponding predicate logic, the question is still open, okay? So if there was some good categorical semantics, which could actually do the same kind of job, then we could know that. So this is what I'm searching for. Whoops. And my idea is, since I think what happens if you say, now I want to do this in a more general setting, then you make a very beautiful general theory, but you don't necessarily understand what is working about it. If you work bottom up from some little thing that you know what you want, then you're more likely to find something. Okay, so my idea is to approach this rather in a bottom-up kind of way, looking at very special situations of binding or quantifiers, where we've seen that duality theory is actually really useful. Okay, and I want to talk in particular about two such cases. And they're both in theoretical computer science. So one is domain theory, and the other one is automata theory. And I can't help myself, but in the last talk, we had two categories that were opposite to each other and that were both monadic over set. And this is very strange, I completely agree. And I think Peter said this is just an incredible coincidence, and that may very well be so. But in fact, in all these cases that I'm talking about, I'm not gonna prove this, but I think very fundamentally they have something like that happening. Okay, so whenever that happens, it may be special, but it's very magical. Okay, something very nice happens. So, so it's maybe interesting after all. But anyway, so let me start by talking about domain theory. So domain theory, this is part of what is known as denotational semantics. And maybe I should even say I want just not domain theory, but a very special problem, which is called solutions of domain equations. And these are things of the form I want some object which is a fixed point for a functor. Okay, and what kind of functor? Well, a functor that's a composition of a bunch of basic constructors which correspond to things in programming languages. Okay, so the most basic one is I want x to be equal to its function space. Okay, this you may know about. It was solved by Dana Scott in the 60s, long time after the lambda calculus, which the lambda is a binder, right? And the point is you have an object, a lambda calculus, where every element is an input to every function, and every element is the function. Okay, and so you have exactly this. And then for the longest time, they could not find a mathematical object like that made sense. So this is what Dana Scott did. And how did he do it? Well, as an inverse limit of a sequence of finite cosets. So what's that? That's a profinite set, and that's a stone space. Okay? I mean, sorry, not stone space in the Boolean sense, but in the distributed lattice sense, or a spectral space, let's call it that. So this, I would say, was started by Scott, but there are lots of other names: Strachey, Smith, Plotkin. I want to get far enough to get to Abramsky, because through all this, it was kind of clear that that duality theory played some role. But what Abramsky did is he actually said, look, this is entirely happening because of duality, okay? And so I want to explain this to you. So he's essentially saying, so I want to explain this work of Abramsky's, which this paper in 91 was called Domain Theory in Logical Form. The logical form meaning the logic is the algebra, which is dual, which is a distributed lattice. Okay? So his idea is, well, let's say, suppose X is a spectral space. Well, then what? Then we can just describe dual of this constructor on spectral spaces. Okay. And then most likely, if it's a nice algebraic thing, it'll be finitary. And then what? In finitary algebras, we have lots of fixed points, right? I mean, we have a least fixed point just starting from the empty set, right? So if we take the free algebra on the empty set for the dual thing, so in other words, this means we take the co-limit of Fn of the empty set, where F is the dual, describe the dual of this, let's call it F. Then this is a fixed point. And of course, the dual of a fixed point is a fixed point, right? So then we found our thing. And this is the point in a topological category, having something that is a fixed point, this is much more complicated, right? But in an algebraic one, it's very easy. This is exactly what duality works for. I mean, this is what why it's useful. Okay, so, and in fact, sometimes this one's trivial. So then that's kind of a problem, like in this case. So then you might want to just start with more generally, if you have some object, some lattice, which fits inside F of it, right? Then you can iterate and you still get a fixed point. Am I saying some nonsense? Then stop me, but anyway. Right. So how does this work? So let me just show you how it works in this case. So we have a first approximation, which kind of rather comes from something we know from modal logic, actually, which is that if you look at, well, that the set of all continuous functions from x to upper via torus of y. Okay, so, you know, Marco's talk was perfect because it introduced everything I want. Okay, so I don't have to tell you any of this, right? He actually talked about lower via torus, but that kind of gives the meat preserving part of Egli-Middlener, right? And this gives the joint preserving part. So no, the other way around. Well, whatever, it's the other half. So this is what I'm doing. So the point is that if you take in general two spectral spaces and you look at all the continuous function from one to the other, this is not a spectral space. Okay, but if you look at all the continuous functions from x into upper via torus of y, then it is a spectral space. Where x and y are spectral. And why is that? Well, because it's the dual of freely adding an implication type diamond or box. Well, so what do I mean by that? Well, if I have two lattices L and M, I look at the free distributive lattice over all symbols, and so all pairs, one from L, one from M. I'm going to denote these pairs as A implies B. I just mean it's like a symbol, right? And I generate that distributive lattice freely on that. And then I mod out by that I want that this operation ends up having the property that the join of a finite set of things implies B, this is equal to the mean. And A meet G is the meet. Okay, does this make sense to everybody? So this object that I get here will not have an implication operation on it, right? It corresponds to like getting one freely by Noetherian induction, right? You start with the elements of your lattice, then you take all single implications, then you should generate a lattice. then do this operation again and keep doing this countably many times. And then the co-limit will be your free implication. I mean, this is not implication in the sense of being adjoint, but only implication type in the sense of having the correct join meet behavior of implication. Okay? Okay, so this one step of adding an implication type box, if that makes sense to you, this is dual to this construction on the spaces. This is an easy duality exercise. Okay, but it is kind of fun in that notice that the basis, the natural, I didn't say here, but I mean in the compact open topology. So what does that mean? I take all sets of functions that map a certain compact set from here entirely inside some open there. Right, and what are the opens of a torus? They are unions of like some kind of box B's, right? So like saying that your open falls inside B hat. So actually the basic opens, they are of this form. All functions so that for each x in A hat, there exists a B so that f of A hat, f of x is contained in B hat, something like that. And this finite union is necessary. And in fact, these sets will not be compact in general. So these are not compact in this function space. So part of proving this here, this duality, is to prove that you can do away with this and you still have a basis. Okay, so these much simpler sets form a basis. So that's a crucial lemma. Is the compact open from the first space is mapped inside box B from the second one, form a compact open basis for the compact open topology. Sorry, in the one case it's the set that's compact open, and the other it's compact open topology, right? So that's very confusing, but there's not much I can do about that. So now the interesting thing is that second step, like I said, xy does sit inside this guy as a subspace. But in general, not as a closed subspace. And therefore, this is in fact not compact, like I said, and so it's not a spectral space. But so the second step is to realize, well, so in fact, the duality theorem is the following. I can look at this F, let me just shorten it, F arrow. If you look at a quotient of that, because what a subspace here, this would correspond to a quotient of the lattice, right? So I can ask which quotients of the lattice get me entirely inside the function space. Okay, so I can say such a quotient has dual inside xy if and only if theta satisfies what I have called, I made this up myself, so it's probably a bad name, but theta preserves joins at primes, at prime filters. So this says that every time you take a point of x of the dual, so this is like a prime filter of L, and anytime you take a point which is in that prime filter, and every time you take a finite subset of M of the other lattice, then you can go down inside the filter far enough that then there exists a point so that A implies join G mod theta is equal to the join of A implies B such that B is in M, G mod theta, or A prime. Okay, so like at the limit, at the prime filter, actually your implication is weird. It preserves joins in the second coordinate. Okay, this is equivalent to falling inside the function space, but in general, you know, there's no best such quotients, no biggest one. But as a corollary, if if the first lattice has enough join irreducibles or join primes, then you can say this in a generators and relation way, because you can just mod out pi, take theta to be generated by P implies join G equal join of P implies B for B and G. You know, so these things where P are the join primes. And then you get exactly the function space. Then F arrow mod this theta dual is the function space. And by the way, having enough joint primes, this is saying exactly that the dual space is what is called an algebraic domain, which is what Scott invented with the Scott topology. Okay, so you fall bang on that when you just ask this question. You don't have to know about Scott's work. You don't have to be a genius like Dana Scott. You just do a little duality theory and it comes out in your face whether you like it or not. Okay, so so I would say here duality theory is very useful. Okay. I probably have talked already infinitely too long, right? But what time is it? How much time do I have? Okay, good. Because this is what I really wanted to talk about. Okay, so this is what I always do to myself. First, I talk about the thing I don't want to talk about so much, and then I have to rush like a maniac to also talk about what I want to talk about. So the other case is algebraic automata theory. And I don't know how much I have to say for this to make sense to you. So the basic object you study are what are called regular languages over an alphabet. Okay, so let's just say A is just a finite set called an alphabet. And reg A are the regular languages over A. This is a Boolean subalgebra of the power set of A star. And what is kind of magical there also is that there are many different ways of saying what those are. Okay, so first it was said by Kleene. These are exactly the subsets given by regular expressions. Okay, so if you don't know what it is, too bad. And there are also the subsets which are recognized by finite state automata. And if you don't know what that is, it's also too bad. There are also the the sets of models of sentences in Gehrke's logic. Okay, and so this is very beautiful that all this agrees, but since I'm talking about logic, I'm just going to say a tiny bit about this one, okay? So the idea is that when you have a word, since I'm Scandinavian, let's look at ABBA. And you actually view this word as a structure for logic. So this, what is the structure? It's 1, 2, 3, 4. It's just and we look at it as having an order, namely the natural order, the usual order of natural numbers. And it has a unary predicate for each letter. And it's just the places where that letter occurs. Okay, so it's 1 and 4. And for B, it's a 2 and 3. Okay, and now you understand everything about that, right? And now the point is that, okay, so what is Gehrke logic? So it just has this symbol and the predicate symbol, the unary predicates for each letter. And then you're allowed to do monadic second order logic. Okay, so you're allowed to quantify over sets of positions. And you're allowed to quantify over positions. Okay? So for example, you can say there exists a position in which there's an A. And this is the models of that. So this we call the language given by this sentence. This would be what, as a regular expression, is given by this regular expression. Right, there's just somewhere there's an A. Okay, but you can also say something more complicated using the monadic part, which you can say, for example, that you have the just even length words. So what would that be? That means you like take two letters next to each other. Star. Right, that's kind of a short description of even length words. And this you can actually say with a formula. So maybe I don't spend the time on it. So if you don't like my talk, you can think about that. But you have to use the monadic part to do it. Okay, so those are regular languages, and so what? So So, computer scientists, they study this class of languages because they correspond to automata. And in fact, also they want to understand how complicated the automaton has to be. And there can be many different automatas giving the same language, that is computing the same thing. And you just care about how complicated is the thing you want to compute, right? So exactly you want to understand how complicated is the regular language. And so you want to look at subclasses that are simpler, okay? And that means you want to understand sub-Boolean algebras of this Boolean algebra. Okay, and very often those are given by fragments of this logic. So what's the most natural fragment to look at if you're looking at monadic second order? First order, right? So you might ask, what are the ones given by first order sentences? And indeed, this is also from the regular setting, very, very natural. It's the star-free languages, they're called, where you don't need to use the Kleene star, but instead you're allowed to use complements. You take Boolean algebra, closed under concatenation of two things. Okay, that's called star-free languages. And that corresponds to the first order fragment. And now you might, especially if you're a computer scientist, then you might want to ask, well, can I check whether something belongs to that or not? If I give you an MSO formula, can you tell me whether it's equivalent to a first order formula? If I give you a regular expression, can you tell me whether I can rewrite it without the star? Okay. So there, for example, if you are further bored with my talk, you can show that the even languages is not star-free. But for example, AB star, that is, you can repeat AB however many times you want. That's a bunch of even length words, okay, but every other one's a B. This is star-free. So it's not so easy. And in fact, the only way that is known, but star-free is this decidable, is this subclass decidable. This is the kind of question they ask. And in this case, the answer is yes. And it's very non-trivial. And the only way to do it is using duality. Isn't that wonderful? So this was done by Schützenberger. In 1965, and of course he didn't know he was using duality theory, but he was. So star-freeness is decidable. And the way he proved that, okay, and so since then, lots of questions of this kind are being answered and are still open, okay? And every time the proofs are very similar to this one, okay? So this kind of blueprint for how it works. And it is a kind of duality story if you look at it from my point of view anyway. So I want to tell you how it works in some general lines. So the very first thing is a very old thing also by Rabin and Scott. And I think Myhill and Rode were also involved more or less at the same time. I mean, it's a very natural thing. So this is in the 60s. that L is regular if and only if what I call BL, which is the sub-Boolean algebra generated when, maybe I should say that first. So the point is, as you definitely know, one way to look at a monoid is as an actions of the monoid, right? And in particular, any monoid biacts on itself, okay? By action, so I mean, it acts on the right and it acts on the left, and those two actions are compatible, right? And because of that, by duality, A star acts on the power set, of course, by inverse image, right? Just by duality. So like, normally you write U inverse LV inverse. This is the language of all words, so that UWV belongs to the language, right? That's the dual action. So this action is central to all this business, okay? And in fact, we want to close under this and invariant under the action. So we close under this division action and then generate a Boolean algebra. And if this thing is finite, then the language is regular. And if it's not finite, it's not regular. Okay, so it's regular if and only if this is finite. So see, you could add another thing there, and it's maybe your favorite, right? And of course, one can just do the dual thing. And this says that the dual of this is finite. And the dual of this is actually, this is what is called a syntactic monoid. Of the language. In other words, you just look at the least monoid quotient of A star, which saturates L. Okay, you want L to be entirely inside one of the equivalence classes. The least monoid quotient that does that, that's the dual of that Boolean algebra. And that's what tells you whether it's regular or not. So actually L is regular if and only if it's saturated by a finite quotient of A star. Okay? So now, a consequence of this, a fairly immediate consequence, once you look at it like this, is that, so this is kind of where I came into the picture with Grigoriev and Pan in 2008. We used this to study all this stuff with duality theory, and kind of a basic, so the one basic observation is that this syntactic monoid of a single language, that's a monoid. I mean, that's a dual space. But more generally then, the dual of the regular languages is obviously the free profinite monoid, right? Because you just take inverse limit of all the finite quotients, and so that's the dual of reg A star is what they call A star hat, the free profinite monoid. Okay. How am I doing for time now? Okay, so I will skip a part now because now I wanted to tell you in more detail how Schützenberger's proof goes. Okay, and the point is essentially that you look at the dual, you look at these monoids. Okay. So in fact, star free, what he showed is it corresponds to aperiodic profinite monoids. So aperiodic means they don't contain any non-trivial groups. Okay, only the, so if you iterate an element, you always just get a single point. You don't get a Z mod n ever. And so in fact, the dual of the Boolean algebra of star free languages is the free profinite aperiodic monoid. And this is what he showed essentially. And how did he show it? He showed it by induction on the complexity of the formula or of doing concatenation product. It's closely related. Okay, so you start with the atomic formulas, and then you show that. Maybe I should at least say this. Where did I put the eraser? If I have a language that's given by a formula in a free variable, now a first order formula, and say it is recognized by, that is, it's saturated by some quotient into a profinite monoid X. Now, why am I saying this thing? It's because one trick they make is to if you have a word with free variables, okay, then you have an interpretation, say X is located at position 2. This you encode in an alphabet by putting zeros in the places where it's not and 1 where it is. Okay, so this is a rich alphabet and it encodes the interpretations, okay? So this way I can actually talk about models with pointed models, but just as being models in a richer alphabet. Okay, so this is already a very interesting thing because the contexts of a hyperdoctrine here are interchanged with predicates that are richer. Okay, you take more predicates and you can encode these things. Okay, so let's say this is encoded there. Then, once you add a layer of a quantifier, then this is recognized by a morphism that you can build from that one. So it kind of does the step of the Noetherian induction on quantifier depth. Okay, and what is this object? This is actually a semi-direct product. No, of Viatoris of X with I don't know which order I want to put them in. But it's a semi-direct product of via torus of x with x, where the multiplication is as follows. You have a closed set K and a point, or didn't call it, and another one and y. Then how do you multiply? Well, you have a funny multiplication here, which is that you do v times y union x times w, and here you do xy. Okay? So you have a semi-direct product that exactly gives you next step in adding quantifier depth. Okay? So, and then you use that to prove that gives you one direction, and then you have to also prove a kind of completeness that if you have an aperiodic monoid, you can decompose it along something like this. So that's the difficult part. But so I don't tell you any more about that proof. But I hope now, can you see anything in common to these two stories? Well, both use duality, but both use very much this kind of Noetherian induction of adding one layer of an operation, right? And what I would say, if you look at F, all formulas of a logic, of first order logic, then you can decompose it in two different ways. You could say, okay, let's look at atomic formulas. Okay, and then F1, all the ones with quantifier depth less than or equal to 1, and so on. Okay? And then in the end, you get the full thing. Or if you're looking at it as a hyperdoctrine, so this is kind of the Noetherian induction way of looking at it. Or you can say, oh, I don't care how deep my quantifiers are. I care how many free variables I have, right? So I look at all the formulas having no free variables. I look at all the formulas having at most one free variable, and so on. And then you get the Leverian way of looking at it, right? Or the hyperdoctrine. And so what I'm seeing in these cases is that what's actually powerful for proving things is this, which is kind of orthogonal to this. I mean, I can't make this precise because I'm not category theorist, but to me, this feels like a co-inductive point of view, right? Because what are we interested in? In the end, we want to understand the sentences. Well, the sentences sit inside every layer of this thing. They're already present everywhere in order to be able to talk about the junction. But they are only fully understood once you understand all these more complicated things, right? Which contain it already. So it's kind of like the intersection of all the things we're looking at, whereas here it's the union of all the things we're looking at. Okay, so we build it little by little. Okay, so let me just end with André Joyal. We started talking about this. And so he wanted very much to understand this automata theory from the point of view of hyperdoctrines. And in fact, a very talented student of mine, Jérémy Marquez, he just started working this past year. And he's already proved a million things and much beyond what I'm going to say here. And he has a paper at Ramix this year that's going to be in November. Based on these internet conversations with André Joyal and I. Okay, and he's looked at this aperiodic monoid case, the star free, that is the first order fragment of Gehrke logic from the point of view of hyperdoctrines. Okay, and let me at least say the punchline relative to that because I might be running out of time. So this is like an infinitesimal piece of this work. Okay, so sorry, but is that in fact the hyperdoctrine which corresponds to corresponding to FO of Gehrke logic is given by a fairly trivial functor which just takes for each, well, so you should look at it as going from finite total orders to Boolean spaces. And for finite total order n, you just send it to the monoid to the n. So this is here, M is a profinite monoid. Then the presentation of the monoid is just this, right? In category theory, you look at it like that, right? 0 corresponds to, no, sorry, the function that sends 0 to 1. This will correspond to the identity element in M. The unique projection of from 2 to 1, this is exactly the multiplication. And so on, right? So this is just the presentation of the monoid. Well, that presentation of the monoid, this is actually what Gehrke calls the Stirling kernel of the polyadic space dual to a hyperdoctrine. Okay, so you take hyperdoctrine pointwise, you can dualize it. You get what he calls a polyadic space. And now you don't really need the whole polyadic space. In other words, you don't need finite sets here. You can just look at interpreting each variable distinctly. And if you know you have a partial order, you can even do it with a total order on your theory, then you can do it like so. Maybe about a few minutes, I will say a little more about that. But let me just for now say that this is a very trivial functor, right? And essentially, this is the dual of the hyper doctrine corresponding to this logic. Okay? So essentially, to get the n types of this logic, you just take the 0 types, which is this free aperiodic, this free, yeah, so in the case of Gehrke logic, this M is the free profinite aperiodic monoid. And if you present it, this is all there is. So it's kind of not telling you anything. You know, the fact that you have all these things, they all just act trivially like these powers of the monoid. Okay? And really the only one where there's something going on is this one, which is the monoid. Okay, and like this one is, you know, when you have n variables, then it's just essentially given by mn, m to the n. Purely and in some kernel sense, but anyway. Whereas to understand how to move between layers here, that is this very interesting, now I erased it, semi-direct product, right? So yes, so I'm out of time. So sorry about that, but really to you, what I wanted to say mainly is that I wish you would try to make some nice mathematics out of this, okay, or some nice category theory out of this decoupage of the formulas rather than just this. I mean, this is important, but this is very useful technically. Okay, thank you.
Thank you very much for a nice talk. Before I ask the questions, could I just ask people not to rush away at the end of the question session, because we're going to have a group photograph before lunch. Okay, now questions.
Thank you very much for the very nice talk. I wanted to say that this has been partially done, if I understand correctly, by Mark Kamsma, and the title of the paper is Type Space Functors and Interpretation of Positive Logic. And what he does, if I understand what you say, is precisely, instead of studying an hyperdoctrine, which is a kind of pre-sheaf into posets, is that is pre-sheaves into spaces.
Okay.
Which precisely, if I understand, correspond to space types for every.
But you know, this is not really. I mean, this is yes. So I think already in 70s, Joyal came up with this idea of polyadic space. Okay, and that's exactly pointwise dual of hyperdoctrines, and understanding the hyperdoctrine like that. Okay, and in fact, in this stuff that I'm saying here in a very haphazard way, I'm already using that. And this is not the issue. Okay, the point is that when you do that to this case, you essentially just get this very trivial functor, which doesn't help you to understand M, right? Well, I mean, if you have the multiplication of M, you understand M. Okay, fine, but you don't get anywhere, right? So this is, it's here, it's not the dualizing of the hyperdoctrine that I'm asking for. I'm asking for carving up the formula algebra in a different way than what a hyperdoctrine would do. This is here, duality theory doesn't have anything to do with that in a way, right?
I'm not sure whether what Kamsma does is to pointwise dualize. That's why
I see.
I would address you to at least check it out.
Okay, yes, I definitely will. Yes, but just from what you said, I couldn't hear. But yes, thank you very much. Yes.
So.
Yeah.
Are there any more questions? Anyone online wanting to put a hand up?
Thank you for the talk. The answer to this question could be just go and read the paper, but I was wondering if you'd put any thought into, like you said, with the monoid, you only need to understand the multiplication in order to get all of the data. I thought whether you'd either you or your student had put any thought into how you might reconstruct this, as you say, trivial functor just from like a truncation of it to the multiplication.
Say the last part again, because I didn't understand.
So you have this functor which corresponds to the hyperdoctrine.
Yes.
But the whole monoid structure is only contained in the multiplication map. So have you any idea how you might reconstruct the whole functor just from this smaller?
Yes.
data?
So that's why I'm really sorry I didn't give more. I should have spent less time on the other stuff. But on the other hand, really, Jérémy should get to talk about this sometime and not me, because it's his work. So maybe it's good I didn't get to it. But yes, this is what he very much does. Okay. And this actually gives some interesting model theoretic information. So I'm kind of downplaying the importance of this, okay? Because yes, indeed, the fact that this is this simple, that it obviously has somehow the zero types easily gives the n types, that's very special. right? And that actually shows that your space of models have a concept of concatenation on them, which is very powerful and very strange. Okay, and this explains this. So this is very much part of that work. Okay, so you're completely right. And this is in there. And yes, I have to tell you to just read the paper because I didn't have time, but this is very interesting. And I'm not saying that there's nothing in this. Okay, in fact, Jeremy does a whole bunch of super exciting things from it, but I'm just saying that relative to, say, proving something like decidability or whatever, okay, this in itself doesn't get you anywhere, whereas if you have an Noetherian decomposition, then this is really useful, okay? So this is just why I'm just I'm not at all wanting to say this is not useful. I'm just wanting to say that I'm observing that in these two cases where duality theory actually was useful, it's rather using that point of view. And if you guys know about that, then I have hope that somebody will do something about it in the future.
Thank you.
More questions?
Hello, thank you for the talk. I just wanted to ask, like, maybe it's off topic, I don't know, but you started with this example with automata, and from there you developed. So my question is, what happens if you change automata for something else? Like you go up to the Chomsky hierarchy or use Petronas or whatever, that does everything explode, or you can still, or I don't know.
So everything does not explode, but
That's nice.
so there are some things that can be done. And in fact, much of what I have been spending the last 5 years on is trying to go to, not to the Chomsky hierarchy, but rather to what is called Boolean circuit languages, because this is very important in complexity theory, right? And there they don't have finite monoids, but you have what Daniela Betrisan and Luca Reggio and I call the Boolean spaces with an internal monoid, which play pretty much the same role and which comes from the same story, and which may allow you to do a similar thing and get decidability of some of all these low-level complexity languages like AC0 and NC1 and so on. So that, I mean, that's what I thought. If anybody else outside of my or our little world of mathematics is going to listen to us, I have to solve a complexity problem or something like that, right? So this is what we concentrated on. Okay. But I think there's, you know, Chomsky hierarchy. Well, I mean, Chomsky hierarchy specifically are not even lattices, right? Because they're only closed on the union, not intersection or something like that. So, but you can also deal with that. But anyway, there are many, many cases that would be very interesting to study, and just very few people who are both interested in that and know enough mathematics to be able to do it. So there's a whole ton of stuff to do.
Cool. Okay, thank you.
By the way, let me make a comment. I'm really so excited to see so many young people. You guys are so young. Or maybe I just got very old, I don't know.
If there are no other questions, anyone online? No? Okay, let us thank my